An alternative to writing rules is to build chatbots that automatically mine collections of human conversations to decide what to say. Most corpus-based chatbots produce their responses to a user's turn in context, either by retrieval methods, using information retrieval to grab a response from some corpus, a response that's appropriate given the dialogue context, or by generation methods, using a language model or encoder-decoder to generate the response given the dialogue context. In either case, systems mostly generate a single response turn that's appropriate given the entire conversation so far, at least for conversations that are short enough to fit into a single model's window. For this reason, they're often called response generation systems. Modern corpus-based chatbots are very data-intensive, commonly requiring hundreds of millions or billions of words of training. Commonly used datasets include transcripts of spoken conversations between volunteers, like the switchboard corpus of American English telephone conversations. Many systems train on movie dialogue, which resembles natural conversation in many ways. Datasets have also been created specifically for training dialogue systems by hiring crowd workers to have conversations, often having them take on personas or talk about knowledge provided to them. For example, the topical chat dataset has 11,000 crowdsourced conversations spanning 8 broad topics, or the empathetic dialogues dataset has 25,000 crowdsourced conversations grounded in a specific situation where a speaker was feeling an emotion. All these datasets, although large, don't reach the size of billions of words. And so many systems first pre-train on large datasets of pseudo-conversations drawn from Twitter or Reddit or Weibo and other social media platforms. It's always necessary to remove personally identifiable information that might appear in the data. The retrieval method of responding is to think of the user's turn as a query queue, and our job is to retrieve and repeat some appropriate turn R as the response from a corpus of conversations C. Generally, C is the training set for the system, and we score each turn in C as a potential response to the context Q, selecting the highest scoring one. And the scoring method is similarity. We choose the R that's most similar to Q using any IR method, TF-IDF cosine, for example. So if we represent Q and R as TF-IDF vectors, then we can find the response in the entire conversation that has the highest cosine, normalized dot product, with the query. So the response to a query is this argmax. An alternative, we can use neural IR techniques. The simplest of these is called a bi-encoder model, in which we train 2 separate encoders, one to encode the user in query and one to encode each potential response. And we use the dot product between the query vector and the candidate response vector as the score. For example, to implement this using BERT, we would have 2 encoders, BERT-Q and BERT-R, and we represent the query and candidate responses as the CLS token of the respective encoders. And then again, we choose whichever turn in our corpus has the highest dot product with the query, and then we just say that turn. The IR-based approach can be extended in various ways, such as by using more sophisticated neural architectures or by using a longer context for the query than just the user's last turn, up to the whole preceding conversation. An alternative way to use a corpus to generate dialogue is to think of response production as an encoder-decoder task, transducing from the user's prior turn to the system's turn. We can kind of think of this as a machine learning version of ELIZA. The system learns from a corpus to transduce a question to an answer. Encoder-decoder models generate each token, R sub t, of the response by conditioning on the encoding of the entire query and the response so far. So response tokens 1 through t minus 1 will help us generate response token t. So to generate the next token, we take the argmax over all possible tokens in the vocabulary of the probability of that token given the query and the tokens we've generated so far. And here on the bottom, I'm showing the intuition of the 2 paradigms. response by retrieval, where we take every sentence in the training set and choose the sentence with the highest dot product with the query, or response by generation, where we build an encoder-decoder model that reads in the query and generates the response one word at a time. In the generator architecture, we normally include a longer context, forming the query not just from the user's turn, but from the entire conversation so far, as in this example, where we have, I finally got promoted at work, congrats, that's great, from the system. The user says thank you, and all of that is an input to the system's response, which is generated word by word. That is quite an accomplishment, and so on. An alternative to the encoder-decoder architecture is to fine-tune a large language model on a conversational data set and use the language model directly as a response generator. For example, in the Chirpy Cardinal system, the neural chat component generates responses from GPT-2 fine-tuned on the empathetic dialogues dataset. Here's a little intermission where the comic author P.G. Wodehouse seems to predict some properties of neural chatbots. Here's what I mean. Basic encoder-decoder models have a tendency to produce predictable but repetitive and therefore dull responses, like I'm okay or I don't know. That shuts down the conversation. Here's some examples from some real chatbots. Pretty dull. A number of modifications are generally required to the basic encoder-decoder model to adapt it for the task of response generation. For example, instead of greedily choosing the most likely, most predictable response, we can use diversity-enhanced versions of beam search or diversity-focused training objectives. Chatbots can be much more interesting and informative if they can generate responses from text knowledge sources other than just dialogue. For example, the chatbot Xiao Ice collects sentences from public lectures and news articles and searches them using IR, based on query expansion from the user's turn to respond to turns like, tell me something about Beijing. One way to augment the encoder-decoder architecture for this retrieve and refine step is to use IR to retrieve potentially useful passages from Wikipedia, and then create multiple candidates by concatenating each retrieved Wikipedia sentence to the dialogue context with a separator token. Each candidate can be given as the encoder context to the encoder-decoder model, which learns to incorporate text from the Wikipedia sentence into its generated response. Chatbots can also be built with architectures that are hybrids of the rule-based and neural corpus architectures, and even use elements of the frame-based structure we'll describe in a future lecture. For example, the Chirpy Cardinal system applies an NLP pipeline to the input and then generates responses with a set of different response generators. Some used fine-tuned language models, such as a GPT-2 language model that learns in fine-tuning to paraphrase content from Wikipedia in response from questions. While other response generators are closer to rule-based. The movie or music generators produce scripted conversation about a movie or musician, such as asking the user's opinion or giving a fun fact. And these generators use regexes and sentiment classifiers to classify user responses and handwritten templates to generate bot utterances. Here's a part of a conversation with Chirpy Cardinal. Notice the use of neural chat, as well as scripted chat modules for movies. In summary, chatbots can be fun and play a useful role in narrow application domains, especially where scripting can be done. But on the other hand, they don't really understand, and the fact that they give the appearance of understanding may be problematic. Rule-based chatbots are expensive and brittle, but IR-based chatbots can only mirror their training data, which, as we'll discuss in a following lecture, can lead to problems. One important next step in research is figuring out ways to integrate chatbot-type abilities into frame-based agents. We've seen the two paradigms for corpus-based chatbots: response by retrieval and response by generation.